Hello, and welcome to The Grid, a monthly platform that connects engineers to critical insights. Today, we're proud to feature a presentation from one of our businesses, Quantic BEI, headquartered in Maumelle, Arkansas. Quantic BEI specializes in high performance sensing solutions, engineered specifically for mission critical applications, where reliability and precision are non negotiable. This session, Precision in Motion, Achieving Unrivaled Performance in Extreme Environments, dives deep into the science and engineering behind motion control systems that perform flawlessly.
So welcome. This is our webinar today, Precision in Motion, talking about how you can achieve unrivaled performance in extreme environments. My name is John Beasley. I'm Chief Engineer here at Quantic BEI. I've been here since 1998. My background is physics and signal processing and electrical engineering.
Hey, I'm Thomas Walsh, Director of Product Engineering at Quantic BEI. I've been with the company since 2012. My background's in mechanical and aerospace engineering, and I've been focusing on developing our nanoseries encoder products.
So our agenda for this webinar, we're going to talk about why precision matters to you. Why is it important? And then go over some basics of optical encoders, kind of what are they, how do they make up, how are they made up, different types of encoders that are out there, some that we produce, and then what kind of precision is involved in some of these high-end optical encoders, and then the basic terms that we use when we're discussing the performance of those encoders. And then Thomas will give us an introduction into our encoders and highlight a particular application where encoders are incredibly important. And then we'll summarize and take some questions. So, big question, why does precision matter? So, one of the applications that you'll find optical encoders is in the turret to hull position determination. So in a tracked vehicle such as the M1 Abrams here, M1A2 Abrams, you want to know where that gun barrel is pointed in both azimuth and elevation. And if you're in a combat situation and you need to be moving across rough terrain, you need to have this gun barrel pointed at a particular threat. Then you have to have a computer control system that is taking out vehicle motion, stabilizing that aim point of the barrel, all while you are moving and all while the threat is potentially moving as well. All of that requires split-second timing. Information needs to be there in a very short amount of time to achieve a particular solution to dealing with that threat. So that's an incredibly important mission, one that we do not take lightly. Another application is up in space. Our encoders are often used for platforms that are taking images of the Earth. Some of those are weather applications, some of those are national defense applications. But when you have a camera system that's in, say, geostationary orbit, 26,000 miles away, and it's taking pictures of a portion of the half of the Earth that it can see, you need to assemble the composite mosaic photo from a series of individual photos, and it requires a motion measurement system that can assemble those pictures with precision so that each pixel of every image overlays on a particular spot on the ground that's known. So that's very important for defense applications and also for weather applications. So a little bit about Quantic BEI. We're located in Maumelle, Arkansas. It's in central Arkansas, just outside of Little Rock. We have about 125 employees and about 70,000 square feet of floor space. The company started over 150 years ago by D.H. Baldwin, who was a music teacher up in Cincinnati. He started selling musical instruments out of a showroom in Cincinnati and decided he was going to make the best piano that can be made, and went off and did it. And through the years, that piano companies started making electronic organs. And in the 1940s, Baldwin had technology for generating tones and musical organs that was adapted to be measuring rotary position for radar applications back in the 1940s. And that's really the origin of the term optical shaft encoder. It's been shortened to optical encoder and even more so to encoder to refer to this general technology. Our portfolio of products here at BEI is the industry's best in class encoders for motion sensing, but we also produce products that are optical scanners that move a line of sight off of a mirror or something like that. And also a wide range of accelerometers that are used for inertial measurement applications. So our legacy in building these products for space applications goes back over 60 years. There's a picture at the bottom of the page there of the very first optical encoder that went into space. It was a contract that started in 1962, and it was the optical encoder for the orbiting astronomical observatory, which was a predecessor to what we know now as the Hubble and the James Webb Space Telescopes. These encoders and other products that we make are precision technologies. They get used in a wide range of applications. We've had some that have gone into planetary exploration, the Galileo, the Cassini spacecraft. They're used widely for Earth observation. Most of our weather satellites have had our products on them. They're used nowadays in laser communications applications. They've been used in robotics, the robotic arms for the space shuttle, for the International Space Station, and for future space stations that are in the works. They've been widely used in radar applications and for optical tracking on missile ranges and missile launches. And then they're also being used for directed energy applications as well. You know, that's using lasers or high power microwaves to disable threats, that are coming in. So as a part of Quantic Electronics, Quantic is a much larger group of companies that includes RF products for RF applications, and also capacitive and energy storage and resistive films. So as a part of this larger group of companies, we have other resources, engineering, design resources that we can connect you with and draw upon for our own applications. So let's talk just a little bit about the basics of optical encoders. What they are sensors that are used to measure the position of some moving mechanism, so you can control it to a desired position or to achieve a desired rate, moving at a certain velocity. So one of the key features about optical encoders is that there's not any physical contact between the moving and stationary parts. They utilize only light and how the optical energy gets modulated by one moving pattern against a stationary pattern. So that's how we use them to determine rotary position. The basic architecture, there's several elements that are shared among many different types of encoders. It kind of starts with, at the bottom here, a rotating shaft that's mounted on a bearing system inside a stator, a static piece. That's the basic mechanism that is doing the moving. And inside the stator, you attach a light source. Ours are typically LEDs. They started out a long time ago being lamps. But LEDs have proven to be much more reliable. And then there's some lenses that collimate or somehow modify the optical bundle that's delivered from the light source. That light then goes up through a code disk, typically, where it is modulated by the patterns on the disk. It gets a spatial encoding in the light that comes through the disk. And then that light passes through a grating that has a pattern on it that's complementary to that on the disc. And the combination of those two is used to generate the position sensitive signals that we intercept that light bundle with a photodiode array, and then pass those small currents generated from a photodiode into a set of electronics where we do the position determination, and then pass rotary position out to our host systems. So there are different types of optical encoders. I've got a few of them illustrated here. On the left, that is a pattern that is typical of an incremental encoder. Incremental encoders come in different varieties, but this is a very simple one where there is one unique position indicated by the one solid block at the top. That's kind of like the home position. And then you keep track of how far you've gone from that position with a track that we call incrementally, telling you've moved a certain number of counts from that home position. Now, those are very simple. They require very simple optics. There's not a lot of electronics that go along with them. However, that when you're keeping track of the change from a certain point, you are susceptible to counting errors due to electromagnetic interference induced errors, or errors that are induced by particle events in the space environment. Radiation can induce counting errors in incremental encoders. So typically do not find a lot of applications up in space because of those concerns. A better solution for harsh environments such as space is absolute encoders. So absolute encoders have enough information encoded on the disk that you can determine where you are with only one glimpse of the disk. I've illustrated that with a disk that is second from the left. That is a pattern that's called a gray code encoder. And you can see on the innermost pattern here, there's a clear aperture on one half of the disk, so you can tell if you're in one half or the other. Outside of that, there's another aperture that covers a different half of the disk. So between the two of them, you can tell if you're in one quadrant or another. And outside of that, there's another pattern that helps you determine which octant you're in, and so forth. This disk will tell you where you are within 256 positions around the disk, and that is called a gray code absolute encoder. There are other types of encoding schemes. I've illustrated just for notional purposes on the next pattern to the right what a natural binary code would look like. You have a most significant bit that tells you which half you're in. The next significant bit tells you which quadrant you're in, and so on. So there's different ways of achieving absolute encodery. The next on the right is a disk that has very, very fine graduations in its outer tracks and coarser graduations in its more inner tracks. And we interpolate several bits of information from each track, then achieve absolute knowledge through a single glimpse of the disk with any of those patterns. There are also encoder types that are used across multiple revolutions of an input shaft and still retain absolute knowledge of position. Those are called multi-turn encoders, and they're used in applications like the tanks, the turreted applications that we mentioned earlier. So how precise are we able to make our optical encoders? We have products that have measurements of up to 28 bits of position information. The former slide just showed you 8. So 28 is a significant improvement in position measurement. Just to try to help you understand what that means, 28 bits means 2 to the 28th counts. That's dividing the circle into over 268 million different pieces. and each smallest piece, the least significant bit of those 28, represents a tiny, tiny dimension on a disk as small as 3 inches. It's a fraction of a micrometer, a fraction of a nanometer on a 3-inch disk. Still a little hard to get a grip on what that really means, but if you think about that in terms of table salt, the typical grain of a table salt, it's not kosher salt, but table salt is about 3/10 of a millimeter. And if you take grains of table salt and you start stacking them next to each other, and you make a circle of table salt that is 16 miles in diameter, you can put a 28-bit encoder in the middle of that circle, and each grain of salt seen from 8 miles away is equivalent to a 28th bit. So these are incredibly small angles. That same, and another way of illustrating that would be using that LSB to line you up between get you into the middle of a hole on a golf green from over 3,000 miles away. So it's not practical on any of those scales. It'd be hard to sink a putt from 3,000 miles away. You don't really want to count grains of salt from 8 miles away. But if you're out in geostationary orbit, 26,000 miles away from the Earth's surface, and say you're trying to, image the weather on a scale that's a mile or two, or if you're trying to measure the trajectory of a ballistic missile from geostationary orbit, then those very, very small angles become incredibly important in those applications. So other terms that we use, we talk about measuring angle in terms of resolution, and we also use a term called accuracy. We discriminate as those as different aspects of rotary measurement. Resolution is the smallest amount of the measurement that you can actually utilize. So you can think about that as a noise floor or the smallest graduations on a ruler. I've illustrated here in kind of a linear presentation what resolution might mean. If you have a ruler that has 12 inches on it, and those are the smallest marks that are on there, if you can distinguish every one of those marks, then the resolution would be 12 inches. So 1-inch resolution. Now, if those graduations on a ruler were not equally spaced, if some were larger than others, you still have a resolution of each inch, but they're not very accurate. They're not each 1 inch. So that's where we bring in the term accuracy, and that is, how well each one of those graduations matches a theoretically perfect reference. So that's two important distinctions in how we talk about the performance of encoders. There's also terminology that's used that kind of gets a little bit backwards. We often talk about, systems that have great performance as having high resolution. Well, that is actually meaning something that, each part is increasingly small. The higher resolution you get, the smaller each part is. High accuracy is also used kind of in the same way. High accuracy doesn't mean large numbers for accuracy. We're really talking about the error being as small as possible. When you are highly accurate, you have less error in your measurements. And then we have another term that's related to resolution. It's quantization. It's just how many different parts are there in a measurement system. So noise, if you have noise in a measurement, then you can have quanta. You can be quantized to a smaller degree than you have resolution. So there's a little bit of distinction between quantization and resolution. Just to try to illustrate the point, one of the examples I give is the sibling problem. If mother bakes a loaf of cornbread or something else delicious, and it's in a circle, there's typically sibling rivalry, and one will want to get the largest piece of whatever's cut. So the parent will let one sibling cut the pie or cornbread, and the other sibling will get to pick the first piece. So the example on the left is where the cutting has not been done in an accurate sense. There are 8 pieces of that, but there are not 8 equal pieces of it. So, if this is something delicious, the sibling number 2 would want to pick the piece in the lower right and not the piece in the upper right. So that's been cut inaccurately. The one next to it, all the cuts have been done very accurately, and that makes for equal pieces. And when you're working with performance applications for optical encoders, you want the latter. You want each piece of measurement that we provide to indicate the same amount of motion. So now that you're familiar with the basics of optical encoders, kind of what they're made up of, and the terms that we use for them, I'm going to hand the presentation off to my colleague Thomas, where he's going to talk about our nanoseries optical encoders.
All right, thanks, John. So we'll now discuss the nanoseries line of optical encoders, which includes a number of different products that we've developed over the past several years, and take a look at some of their performance and key attributes. And then at the end, we'll look at an application where we've used this nanoseries technology with some of our legacy technology to develop a couple of new products for the U.S. Army. So the nanoseries line is actually a grouping of several different products that we've developed and kind of riffed off of each other over the past about 10 years. This group of products has a few key attributes or a few common themes, which is why they're grouped into the nanoseries grouping. And the first of which is that they're all on the extremely high end of position and pointing control. So these are ultra precise encoders, up to 28 bits of true absolute position. True absolute meaning that when you ask the encoder for an angular position, it responds by turning on the light, shining that light through the code disk, and then computing that position without any knowledge of the past, regardless of power down, power back up, no motion required. It truly calculates angle based on code pattern on that disk. The accuracy of these devices is as high as they can be. We're down to 1 arc second level accuracy over the entire spectral bandwidth of what we can examine. So these are extremely precise devices. The second common theme is that they're all kit style encoders. So the kit style means there's a code disk and a read head separately, and it's installed by the user at the user's facility onto their axis of rotation or their mechanism. And so it's really neat that these two things can exist together. That's not trivial. Typically for a kit style, you have to make some concessions. You have to give up a little bit of precision to allow folks who may not be familiar, with optical encoders to install these and get them operating on their systems. Typically, the ultra precise devices are installed by encoder engineers and technicians. So this last common theme is why and how we're able to offer an ultra precise kit encoder, and that is the auto calibration and alignment capability that these devices all come with. So when we sell a kit encoder to a customer, they can enter that alignment mode and then do that installation themselves with active feedback to get to extremely precise centrations of the code disk to the axis of rotation, and then also position that read head in the exact right location. Finally, the encoder is put into auto calibration mode, and by rotating the disk under the read head through one or more rotations, the encoder will self-calibrate and correct for all of the inconsistencies, all errors. It's completely forgiving on, a little bit of alignment or misalignment. And so that allows us to sell such a precise sensor in a kit form factor. So this slide looks at a number of different products to kind of display all the different forms and sizes of the products in the nanoseries line. On the left side, you see Tracker and Aura, which are kind of the earlier versions of the nanoseries encoders. So it's a common read head form between Tracker and Aura. The Aura system has remote electronics. It's got a lot of functionality in those space electronics in that remote box. And then as we've through the years developed the product lines, we came up with smaller read heads, the MKE micro kit encoder on the right hand side, just a little bit different form factor, but still a kit encoder. As you can see, the code disk size is something that can vary down between 1 inch and up to over 18 inches in outer diameter. So we can find a form or a size that fits your application just with these standard products in most cases. So now we'll look at these different read head sizes. As I mentioned, the ARA tracker, and then a third terrestrial encoder, the AIM2, they all started with the same read head size. So this was nice because we can switch customers around from, say they wanted to start with an AIM2, a terrestrial encoder with no space electronics on a demonstrator. And then depending on the style of mission they have, they may need a tracker or an ARA system. And so they can bring in and swap those different read heads out. It's different electronics, but the same mechanical interface. And then we can see as we move through, there's Tracker Lite, which is a smaller version of Tracker. We'll get into through-hole MKE, and then the micro kit encoder, or MKE, which is a 1.5 inch diameter. It's a round read head that fits completely over a code disk. It's still a kit, but you can't see the disk on the inside there. So this slide depicts a matrix showing all of the different technical specs and performance specifications that the encoders exhibit. I won't get into detail on all of these, but put this here to show the breadth and depth of our product lines in terms of technical requirements. We cover the gamut on resolution, accuracy. So we go from the ultra high to the just the somewhat ultra high regime, if you will, in terms of performance with this slide. So along with covering all of the different performance requirements, we also range our products in terms of mission assurance. So we like to talk about a tiered product offering, and that is offering a product such as Tracker, for instance, that comes with electronics and a mission assurance program that's suitable for prototypes, demonstrators, or Class D, Class C missions. And then we also scale that up to the highest level of mission assurance, Class A, B types of missions, critical stuff, or the higher radiation missions out in MEO and GEO. So going from left to right in the columns, we see commercial space plus, and then our space level 1 and 2. So the commercial space products are versions of these encoders that have commercial electronics or COTS electronics. They're still built in our clean room to IPCJ standard 001 solder workmanship, but they are not put through the rigors and the test campaigns that a higher level product may undergo. They also do not have radiation assurances at the part level, but we have done radiation testing on examples of these encoders, and so they are rad tolerant, and they're capable of operating in LEO environment, and are great for demonstrator missions, or even if you're planning to move on to the higher level products, they're great as a prototype in the laboratory. The second option is our Commercial Space Plus, and this is somewhat of a new mission assurance level for us. Commercial Space Plus takes those commercial space products, and we build example encoders with batches or lots of ICs that we've pre-procured and put in our stock room, and then expose those example encoders to the radiation environment and ensure that all the ICs on a lot-by-lot basis are acceptable. And so we can sell encoders built with ICs from those same lots. And so this is kind of a careful COTS or a safe COTS way of assuring a radiation tolerance for these products. The highest level of mission assurance, product assurance that we offer are our space level 1 and 2. So these are encoders like ARA, Tracker, or MKE that are built with your typical ceramic ICs that are all qualified either to EEE N002 level 1 or 2, or Jan S QML parts. And so these go through a full space level ATP after they're built, including vibration, shock, thermal vacuum bake out, all of the typical space tests that we run those through. And then one feature that I touched on that allows us to sell kit encoders of such high precision is the alignment mode. So this is a feature that turns our rotary optical encoder into a three-dimensional sensor. This feature allows us to sense both radial and tangential motion between the code disk and read head. So this enables folks, us here at BEI, but also our customers who we sell these encoders to align the code disk to the axis of rotation very precisely, and then bring the read head on and align that to exactly where it needs to be to allow the encoder to calibrate and to effectively deliver the 24 or 28 ultra accurate bits of position. This feature also is really neat for our customers to look at during the build process. If after they've got the encoder installed, they want to look at how the axis of rotation or their mechanism is behaving to different outside forces, such as temperature or loading, or G loading if a mechanism is turned on its side or upside down. So this is useful even on orbit. Customers who want to go back and look at the health of their mechanism, how that axis of rotation is behaving over time, if it's aging, if there's jitter or something that's coming into the axis of rotation and causing a relative motion between the code disk and read head, these sensors can sense that. So the little picture here depicts, the direction of the radial sensor, what it can sense, and then also the tangential sensor in the blue arrows. All right, so the first product I want to discuss is our ARA, which is our flagship optical encoder for space applications. This is our highest performance and highest product assurance product in the nanoseries line. It's a 28-bit angular sensor. Accuracy is down to 1 arc second level, or even better over limited ranges. ARA is a modular system, so we can have up to 4 read heads connected to a remote electronics box that can support up to 4 individual axes, or in a redundant sense, you can have 2 axes with 2 read heads each. The remote electronics is also can be redundant. You can stack boxes to support the different mission profiles. The components used to create this system are all rated to at least 100K rad TID. They're all the highest level of quality, all level 1 or JNS components. And ARA also supports our auto calibration and alignment features, and can correct for errors such as the first harmonic disk centering error if the disk is not perfectly centered to the axis of rotation. So next is our tracker encoder. Tracker was developed really to answer the call for the new space push or the commercial space marketplace. It's a little bit lower performance at 24 bits of resolution, and the accuracy takes a step back. But Tracker is great for folks who want to have that scalability from commercial space, prototype level with COTS components, up to level 1, level 2 components for the higher requirement missions. So there is no remote box with Tracker. All of the electronics are in that little read head. And this is a minimum 50K rad rated device. Tracker, of course, comes with the standard auto calibration and alignment mode, standard on all of our nanoseries products, and supports a wide variety of code disk diameters. So we sell a lot of these in anywhere from labs, terrestrial situations, LEO, and then for the higher quality folks up at the GEO orbit. All right, so the micro kit encoder, or MKE, is our smallest flight-worthy optical encoder for space applications. This encoder is an 18-bit resolution, 30 arc second angular sensor, and all the electronics fit into this tiny little read head down at 1.5-inch diameter. This looks a bit different. It's still a kit encoder. If you can see in the bottom picture, you can see the code disk It's 1 inch diameter, and when it's mounted, it's fully enclosed inside of the reed head. That code disc is a shaft clamp style mount, so it slips over the end of a DC motor or a small mechanism with various shaft size options available. The electronics are scalable, just like on the Tracker product line, from commercial or COTS components up to the level 1 or level 2 product assurance level with a 50K RAD TID rating. And it's the same communications protocol as a Tracker system, so it operates in much the same way, which is great for if you have a system that might need both Tracker performance on one axis and this MKE performance or size on a different axis. So these next two are form factor changes, if you will. We've taken the Tracker and the MKE, which are popular encoders, and reshuffled the deck on their mechanical arrangement to offer a couple of different products. So this is the Tracker Lite, and what we've done here is taken the Tracker and just eliminated the option for level 1, level 2. So this is COTS only components, which allows us to reduce size, weight of the reed head, and the cost to get down to this small reed head size, about 1 inch cube. It still supports all the same code disk sizes from 3 inch up to 18 or more, and it operates in exactly the same way as Tracker with the same communication protocol and performance specs. And this last product, the through-hole MKE, is the same electronics as the COTS version of MKE, but we've gone back to that more traditional edge mount kit style. So the reed head mounts from the edge of the disc, just like all the other products. The disc sizes here are filling in that gap between MKE and the other products, so 1.5 up to 2.5 inch outer diameter. And it's the same communications and performance as MKE. All right, so now we'll take a look at a really neat application that we developed some products for. They're based on both the nanoseries technology, the MKE in particular, and some legacy products of ours. And so we've been able to merge kind of our current state of technology with some of our past, our great heritage, and come up with some new products for this exciting application. So the Next Generation Combat Vehicle program is it's an R&D that the U.S. Army is carrying out to upgrade and modernize ground vehicles to support the warfighter. So BEI has a long heritage of offering precision optical encoders for the turret systems on ground vehicles such as those shown on the screen. As the NGCV program was taking off, we took note and decided that BEI should participate in the program. We took it upon ourselves to modernize a couple of our products and offer them for this effort. And we chose the micro kit encoder as the technology to start with and place into a couple of different form factors for the azimuth and elevation angular sensors for this NGCV effort. And ground vehicle market is a really great market to be in. It requires some robust optical encoders because it's extremely rigorous environment in both mechanical, thermal, and survival requirements. So it takes an incredible amount of precision as well and reliability, as these sensors are part of the fire control solution for these ground vehicles, the tanks and gun mounted vehicles. So our first offering for NGCV is the azimuth encoder. Take a look at. Now, this is a housed encoder. It's an optical encoder built on its own bearing assembly. This one has a gear interface. Now, John mentioned before about a multi-turn encoder. That's exactly what this is. So the turret of a ground vehicle is a fairly large diameter typically, and they're driven by a gear in most cases. But there is no tangible axis of rotation in the middle to mount an angular sensor upon. What we've come up with is a gear interface that mounts to that driving gear off axis. And then as the turret rotates and turns that gear, say 10, 12, 15 times, it rotates the code disk inside of this azimuth encoder just one time to match up with the angle of the turret relative to the hull of the ground vehicle. So this device actually has two MKEs inside, with one code disk rotating with a 1-to-1 relationship with the turret, and the other with a 16-to-1 relationship with the turret, which provides the highest resolution up to 24 bits and increased accuracy. To round out the NGCV offering, we have our elevation encoder, which is a single turn shafted or shaft mount housed encoder. So one revolution of the shaft just turns one MKE code disk. And this is intended to be mounted on the cannon trunnion or cannon elevation axis of rotation. So this provides 24-bit quantization or 18 effective bits of resolution on the output. And as you can see, it's a very ruggedized solution. The MKE, which is a pretty small encoder, wouldn't be able to survive the extreme shock and vibe requirements that the U.S. Army lays out for these types of sensors. So it's a very robust solution, and we believe that the NGCV encoder offering here for azimuth and elevation sensors meet the requirements to serve our U.S. Army.
All right, so thank you for that, Thomas. That was an excellent presentation about some of our product details and particular applications. So what do we want to leave you with about our presentation today? We want you to remember that our products offer you the reliability to work when you need them to work. We've shown that our products are solutions for missions across all domains: space, air, land, and sea. The precision our products offer give you the ability to have high performance motion control solutions. And then we offer a wide range of products that are very versatile, can be adapted to a number of applications. And we also bring with us a deep well of knowledge of how to use these products and solutions that ends up being a very valuable asset for our customers, both the products we bring and the experience and knowledge that we bring. So we want you to remember that our products are reliable, they're precise, and we bring a lot of experience to the game. So with that, we thank you for your time today, and we want to open it up for questions and answers and knowledge that we bring. So we want you to remember that our products are reliable, they're precise, and we bring a lot of experience to the game. So with that, we thank you for your time today, and we want to open it up for questions and answers. So one question that came in was regarding the coordinate system that we use in our encoders, and answer to that is the most simple way to think about a coordinate system for a rotary encoder is just portions of a revolution. What fraction of a revolution are you presently occupying, or have you traversed? From there, you can think about a revolution as being defined by units in radians or units of degrees, minutes, or arc seconds. And there's just conversion factors that you use to get between any of those unit systems. But it's most simply thought about as fractions of a revolution, and then you can convert that to whatever angular units you wish. The question was about incrementals, encoder susceptibility to noise. Can you do anything that can help reduce that? And the answer is yes, you can. But some of the problems of being up in space are atomic particles that have been hurled out into space by our sun, or that have originated in supernova far away, and you're getting near relativistic ions being hurled at you, and they smash through any shielding that you have, or pass through the middle of the nuclei in your shield materials, and still end up creating showers of secondary particles on your electronics. So up in space, these single event effects are very problematic for any electronics and sensor systems. And that's, there's not a lot you can do about that. So that's where the virtues of absolute encodery really kind of present the best solution for true knowledge of absolute position. There's other types of encoders that are, you have a pseudo random code that are, if you move around enough, you can figure out where you are, but they are also susceptible to, single event type of effects. So the schemes that we employ with true absolute knowledge on the code patterns are really optimal for the space environment.
Thanks, John. So the next question was regarding our alignment mode and the different types of alignment mode that we have across the product line. So some of our products like Tracker and MKE, they have just what we call radial alignment mode. So they're not quite as capable as ARA and the AIM2 encoder that have the radial plus tangential alignment mode. So the difference between these, like for Tracker and MKE with just radial, it can sense in a radial direction the distance between the read head and code disk. And it's really sensing the distance away from nominal or zero misalignment. And so it does this, to a high degree of precision down to somewhere in the micro-inch resolution range, over a range of plus or minus 4 thousandths of an inch. And so we can use this to center the code disk and align the read head radially really well, but we don't have information that lets us align the read head left, right, or tangential against the disk. Now with ARA and AIM2, the encoders that do have both sensors on board, radial and tangential, we can see the radial sensor as well as the left, right, or tangential misalignment between code disk and read head. So you can imagine as the code disk is rotating and it's running out because it's mounted a little off center of the axis of rotation, you'll pick up radial and then it'll move to the right and then farther away and to the left. And so you can really see the full motion of the axis of rotation and of the code disk as it rotates. The next question was about a comment I made on how we can get better accuracy when we're examining just a smaller portion of the disk. So the question was, how can we achieve higher precision over a limited range? Well, really, it's not higher precision per se. It's not any higher resolution than we achieve over a limited range versus the full 360 degrees. The resolution of the sensor is still the same. But if we only analyze the accuracy, the error experienced over, let's say, 10 or 20 degrees of motion, that error on the whole is far less than the error you might experience if you were to rotate for a full revolution. Over that full revolution, you're going to experience, the entire run out of the code disk, and just more error content that's there. So when we're just looking at 10 or 20 degrees, our error metric, that drops down to a few tenths of an arc second RMS. What's the greatest obstacle for further increasing the precision of our encoders? I think that there's kind of two things I'll say about this. We can go to a higher precision, but that makes the optical encoder harder to build, harder to use and install, and harder to maintain over the rugged environments. So we're kind of at a place now with the technology that we have enough resolution, precision, really for most applications that come our way. If we took it too much further, we're dealing with dimensions on the code disk and alignment tolerances that are so tight, it would make it really quite difficult to use. So what do you think, John? I mean, is it electronics that kind of limit our noise floor for our products?
Yeah, the electronics are part of it, but we've made great strides in that part of the solution space. We've also done we've had products through the years and internal products that are using interferometric optics, to achieve greater resolution of just the optical signals that we're intercepting and decoding. So there's other ways that we can tackle the problem of increasing the precision, both optically and through improved noise floor of your electronics. But I agree with you that there's kind of a practical limit in the applications where you can use those things. Our 28-bit encoders, if you're using a 3-inch disk to get 28 bits, I mentioned that the quanta, that smallest bit, is less than a nanometer on that disk, and there's a seismic noise floor most everywhere you go that exceeds that type of metric. So being able to use all of those bits terrestrially, you kind of run into a performance limit just practically of it is the most sensitive detector that you've got in your system of any motion. And one of the first phone calls we've got that we typically receive for uh, high resolution encoders is, why is this so sensitive? It's the way it's spec'd, it's the way it's built, and the way it's used is really kind of at the limits of what most people can comprehend in their systems.
If you have any follow-up questions, I encourage you to reach out to John or Thomas via quanticbei.com, and they'd be happy to help you.